Welcome back. So let me begin by giving a summary of what we did in the last lecture. So first thing is we talked about series and parallel combination of resistances. So one of the things that I wanted you to understand is that these nomenclatures have specific meaning. In fact, I gave you an example of a situation where a resistance combination looks arranged parallelly, but they are actually a series combination. So the way it works is this, that we defined parallel combination as a collection of resistances in which the arrangement is such that the voltage across any member of the combination is the same. So the way it works is this. Supposing this is a point A, so I have one resistance here, another resistance here. I could have any number of them actually. Third resistance here. So let's just call them R1, R2, R3. So what we are saying is this, that the drop in the potential, if you go through the resistances, whether you go through this or that, is the same, delta V. So this would mean that since the values of resistances are different, the current in the branches would be different. So we will say that voltage across each member is the same. But current carried is different. So voltage across is delta V. Supposing here I have I1, this is I2, this is I3. So expressions for delta V are either I1 R1 or I2 R2 or I3 R3. They are the same. So when you look at a combination, the way to recognize whether it's a parallel combination or not is to check whether the voltage drop across various members are the same. So that's one. We next defined what is called a series combination. So that's of course a much simpler one. So there what happens is this, that there are various resistances in that combination. Let's again call them R1, R2, R3, and this is the point A to B. Now this is defined as a combination in which the same current passes through. Same current passes through. As a result, since I is the same and here R's are different again, so therefore this is IR1, this is IR2, this is IR3, this is the drop across them. So therefore, the drop delta V1 across this, delta V2 across this, delta V3 across this. So the net drop across AB, so let's call this VAB, is I times R1 plus R2 plus R3. So let us return to the example that we had started working out towards the end of our last lecture, but couldn't complete it. So supposing I have a combination of resistances like this. This was a 21 volt battery, and what I had there was a switch which was initially open. So let us number them. Let's call this point A, this is B, this is C, D, and E and F. So what we said is this, that when this switch is open, so this section doesn't actually do anything to the circuit. But look at this pair of points. The voltage drop across CE, because C is connected to this side, E is connected to this side of the battery, is 21 volts. Voltage drop across DF is also 21 volts. We had given some numbers to represent so this was 4 ohms, this was 12 ohms. So I called this R1, called this R2, and this is R3, and this is R4. So R4 was 8 ohms, and R2 was also 8 ohms. Let's look at what happened there. So if you look at it, the current comes out from this positive terminal, and part of it goes here, part of it goes there. So let us call this, it's getting cluttered up, so let me use a slightly different ink. Let's call this I1, and since this is passing through R3, let's call this I3. So look at this, if a current I is coming through this, then clearly your I gets divided into I1 and I3. And because current is nothing but flow of charge and there is no accumulation of charge anywhere, so rate of flow of charge here plus the rate of flow of charge there must be equal to the rate of flow of charge which came through the circuit. So since we have said that the drop across this is the same as 21 volts, so what we notice is the following, that here, since this part of the circuit doesn't matter, so R1 is in series with R2. So in branch C, R1 is in series with R2. So therefore, this circuit has a net resistance of 4 plus 8 equal to 12. So let's call this R12, that's equal to 12 ohms. And likewise, R3 is in series with R4. So let's call this R34. That's equal to 8 plus 12, which is equal to 20 ohms. Now, having done that, you notice that this circuit is now reduced to a circuit like this. So this is 21 volts, this is 12 ohms, and this is 20 ohms. But this 20 and 12 are now parallel. So we call this R12 and we call this R34. So we say R12 and R34 are parallel. Remember the formula for the parallel combination that I gave, equivalent resistance. So the equivalent resistance of this combination is given by 1 over Req equal to 1 over R12 plus 1 over R34, and that's equal to 1 over 12 plus 1 over 20. And if you invert this, Req will turn out to be equal to 15 by 2, that is 7.5 ohms. So what I now do is this, I draw a further equivalent circuit which is at 21 volts here, and a 7.5 ohms there. And now I can easily find out how much current I was there, because that is what is coming out. So which tells me that the current I which the battery supplied to the whole combination is given by 21 divided by 15 by 2, which if you work out, it will become 42 by 15, which is 2.8 amperes. So therefore, if you look at the original circuit now, so what we said is just go one step back. Now if you go one step back, what you realize this, that this I which came in, which was 2.8 amperes, got divided into this part and got divided into that part. So therefore, the current in this section, so this was 21 volts, and we showed that this is 2.8 amperes. This is 12 ohms, this is 20 ohms, we call it I1, we call this I3. So this point is C, D, E, F. This was the situation where the A, B were not connected. So in this case, the drop across CE is the same as the drop across DF is equal to 21 volts. So delta V CE is delta V DF is equal to 21 volts. So therefore my current I1 is 21 divided by 12, that is R1 plus R2. So that's equal to 1.75 amperes. I2 is equal to 21 by 20, that's equal to 1.05 amperes, which of course agrees with our original current, which is 2.8 amperes. Now you can use this to find out the potential drop between the points C and A. Remember that A was here. This was the point A. So now you know I1, the R1 was 4 ohms. So I1 times R1 is the drop across C to A. C was at 21 volts. So the point A will be 21 minus I1 times 4. You can easily calculate and find out that this VA was equal to 21 minus I1 R1, that's equal to 21 minus 7 by 4 into 4, that's equal to 14 volts, and VB equal to 21 minus I3 R3, that's equal to 21 minus 21 by 20 into 12, that's equal to 8.4 volts. Now let us close that switch. Now when you close that switch, the entire character of that circuit changes. So let's look at what is happening when I close that switch. So let us redraw that picture again. So this was a 21 volts battery. I had a 4 ohms here, R1, just indicate without. This is R2, which was 8. On this side there was a R3, which was 12, and an R4, which is 8 again, and I had this switch connected. So this was CD, this is A, this is B, this is E, this is F. Now let us look at what type of a combination is this. First thing you realize is this, that this, when you close the switch, point A and point B, because this is a short. This is a short because there is no resistance across this. So therefore, VA must be equal to VB. Likewise, VC is equal to VD and VE is equal to VF. Since C and D have the same potential, A and B have the same potential, this tells me that this 4 and 12 are parallel. If you recall, I had said that the way to recognize whether some resistances are in parallel or not, you have to find out whether the potential drop across them is the same. We can redraw the circuit in the following way. So remember that I had the 21 volt drop here, and the circuit is essentially equivalent to the following situation. This is R1 and this is in parallel with R3, and here I have an R2 in parallel with R4. The points with reference to original labeling is this is a point C or D as the case may be. This the point is A, this point is B. This is A prime, this is B prime. They are the same points really, A or A prime. So let's say A equivalent to A prime, B equivalent to B prime. And the last point is E or F as you desire. So since R1 is parallel to R3, my resultant is R13 equal to R1 R3 divided by R1 plus R3, and that's equal to 48 divided by 16, that's equal to 3 ohms. Likewise, R2 is parallel to R4, and that leads to R24 equal to R2 R4 divided by R2 plus R4. They were all the same resistance. So this is 8 into 8 by 8 plus 8, which is equal to 4 ohms. So at that stage, my circuit is this. I have a 3 ohms here, which we called as R13, and I have a 4 ohms there, which we called as R24. And this was 21 volts. Since R13 and R24 are in series, my net resistance here is 7 ohms. So therefore my current is 3 amps. Now notice this thing. This point, this was my point C, this is my common point A or A prime, and this was my common point E or F. So since 3 ampere current is reaching C, then my drop across CA is 3 into 3, that is 9 volts. And drop across AE, CA, and this is AE, is 3 into 4 equal to 12 volts. Now you return to the original circuit. Let me redraw the original circuit again. So my current in this section CA is not equal to the current in this section CB. In fact, if we remember, we called this one I1, this one I3, and this was I. So my I1 plus I3, that must be equal to the current supplied, which is 3 amperes. And we have seen that the drop across CA is equal to 9 volts. So I can easily calculate how much is the current I1. So current I1 is obviously 9 divided by 4, this was 4 ohms, which is equal to 2.25 amperes. Is equal to 12 volts. So if we call this I2 now, so that would be equal to 12 divided by 8 ohms, that was the resistance of this. So that's equal to 1.5 amperes. So you notice that 2.25 ampere is coming in at C, but 1.5 ampere is going out through this section. So therefore, there must have been a current in this section. So IAB, which is the difference between the two, because there cannot be any accumulation of charges there. So therefore, IAB must be this minus this, that's equal to 0.75 amperes. Now what you can do is, you can do a consistency check by repeating this calculation here. So this drop was 9 volts. You can find out how much is the current here, and then similarly you can find out how much is the current there, okay, and you will find that the result would be the same, that this minus this would be the amount of current that is flowing into the section at AB. So this gives you an example of how to calculate things in which we have parallel and series circuits. So let me show you some little complicated problems. Suppose I have a situation like this. Now what I will do is that instead of drawing wiggly lines for resistances, let me for the moment just draw them like this, but I will tell you where the resistances are. So this is A, this is B, and what I am saying is these are all resistances, and the upper part each is 1 ohm and the lower part of each is 2 ohms. The connecting wires are of course not are resistances. So let us look at what can I say about this circuit. So look at this situation. So notice that here I have these two, because there is no connecting. Remember that the connection to the circuit, which means connection to external battery or whatever is the source of EMF, is between A and B. So therefore, if I look at this section and this section, this is in series, because whatever current comes through this, that must come back through this. So 1 and 1 are in series. Similarly, 2 and 2 are in series. So therefore, this section that I have got here, these are connected to the next one. So this is 1, this is 1, this is 2, this is 2. So this is the same as a 2 ohm resistance being parallel to a 4 ohm resistance. So I can redraw this circuit like this. And then of course each of these sections will be connected to the next section and 4 of them will be there. So this is 2 ohms and this is 4 ohms. Since 2 ohms is in parallel with 4 ohms, I get the equivalent resistance to be equal to 2 into 4 divided by 2 plus 4. So that is equal to 8 by 6. So which is equal to 4 by 3 ohms. So this is nothing but a single 4 by 3 ohm resistance. And 4 of them are connected in series. So therefore, net resistance of this combination is 4 into 4 by 3, which is equal to 16 by 3 ohms. Let me take another example. I'll consider an infinite resistance network. So the network is like this. You have resistances, all of them have the value R. And they are connected also by resistances R. What is the effective resistance of such a circuit? Now, in order to do that, you have to make an observation. Remember, I have said it's an infinite sector. So supposing there were an end to it. Now, what do you mean by end of an infinite resistance section? Imagine the number to be n, which is very large. So look at the last section. So this is, let us suppose, the last section. See, if I were to cut this like that, then whatever remains there has the same structure as the other one, the longer one. And since I have said it is infinite, it won't make any difference at all. So therefore, if my equivalent resistance for the whole network is Req, then after I cut it out, what remains is also Req. You take out an identical section from the end of an infinite network, you are still left with an infinite network. So therefore, the Req, which is the equivalent resistance what I am looking for, is equal to the equivalent resistance of the infinite section to the left of this red line. So this is equal to Req plus this sector which I have marked with red. Now let us look at what this actually means. Now notice, what has happened as a result is this. This Req section has become parallel with this R. So Req is parallel to R. So therefore, the effective resistance that is coming from this section and that section, this R. So that is simply equal to, let's call this Req, the effective resistance Req into R divided by Req plus R. So this amount, so I will draw this again. So we are saying now that I have a resistance here which is this quantity, that is, let's call this Req prime. And of course these two R's. But this circuit is a simple circuit, which is R and Req prime are in series. So therefore, this is equal to Req prime plus 2R. And Req prime I have already obtained a relationship which is Req R divided by Req plus R plus 2R. Now if you solve this, this leads to a quadratic equation. So let me write down Req prime, Req R divided by Req plus R in the denominator. I have to add this to 2R and that's equal to Req. Let's simplify them, which is Req R and 2R are equal. So it is 2R square plus 3Req in the numerator, and denominator I cross multiply. So I get Req square plus R into Req. So therefore, Req square minus 2R Req minus 2R square is equal to 0. So the solution for Req is 2R plus or minus square root of 2R whole square, that is 4R square, plus 4 into 2, 8R square divided by 2, and that's equal to 2R plus or minus, take away a 4, so I get 2 times square root of 3 times R divided by 2, which is equal to 1 plus or minus root 3 R. Obviously, I pick up the positive sign, so equivalent resistance of this infinite network is 1 plus root 3 times R. Once you know the value of R, you can calculate. Now, this idea that series resistances and parallel resistances, I can find effective formula, can be used to solve problems which do not look like the standard resistance network problem. So let me give you another example. Let us look at a resistor which has this shape. There is a conical shaped resistor. This section has a radius A and this section has a radius B, and let us suppose that the length here is L. Now, how do I find out supposing the material has a resistivity rho? How do I find out what is the resistance of such a sample? Of course, we assume that the same current is passing through this each section, which is circular in nature. So let us look at this. Now I can first assume or looking at what is the radius of the circle at a distance x from one of the ends. So this is what I am looking for. This distance is x. Now this is linear, so we write down the radius of that section at a distance x is given by a plus b minus a over L multiplied by x. So supposing at that distance I consider a small cylinder of width dx. So my resistance of that section dr at x will be given by rho times the length, which is of course dx, divided by cross sectional area, which is pi into this radius square, which is a plus b minus a by L x whole square. So what I do is this: to find out how much is the r, rho over pi is of course a constant number, I integrate this quantity dx divided by a plus b minus a over L times x whole square, and the x is from 0 to L. This is a straightforward integration. I don't go through every step of that integration, and you can find out immediately that this quantity is given by rho by pi into b minus a over ab, and that's equal to rho by pi L times or L over ab. L is the length. You notice that supposing a were equal to b, then I will get the resistance to be given by rho L by pi a square, which is what I expected for a normal cylindrical conductor. Another example I will give you, where again I use the same principle of adding up resistances, but this time with a slightly different application. Suppose I have a stack of aluminum and graphite. So let me draw that. So this is a stack of aluminum followed by a stack of graphite. Having the same cross section. So let's say this is the length of aluminum section. This is the length of carbon or the graphite section. And the data that is given to us are the following: that the resistivity for aluminum at 0 degrees is 2.75 into 10 to the power minus 8 ohm meter, and its alpha value, alpha aluminum, that is the temperature coefficient of resistivity, is 0.004 per degree centigrade. The corresponding data for graphite is 5 into 10 to the power minus 5 ohm meter, and alpha for carbon is negative 0.0005 per degree centigrade. Now you see, this is essentially a series circuit, because any current flowing into, let us say, aluminum will also pass through the carbon if there is a complete circuit. Now what we are looking for is what should be the ratio of the lengths of aluminum section to the carbon section, so that the temperature coefficient of the combination will be 0. Now what it means is this, that supposing I am looking at the resistance of the aluminum section at a temperature T plus the resistance of the carbon section at a temperature T. So I get resistance of aluminum at 0 degrees into 1 plus alpha Al into delta T plus resistance of carbon at 0 temperature, 1 plus alpha carbon into delta T. Now, what we are essentially looking for is this, that what should be the length of the ratio of the length of L aluminum to L carbon such that this quantity is independent of temperature. What it means is I am looking for RAL plus RC that should be identical to RAL0 plus RC0. Now, if this were so, what I require is that the contribution from the temperature dependent part of these two should cancel. So, what it means is R aluminum 0 alpha aluminum times delta T, I should have written as delta capital T, equal to minus R carbon alpha carbon into delta T. Now, remember, my resistance is proportional to the length and inversely proportional to the cross section, but in this case my cross section is the same. So, what I require is that alpha aluminum times, well, I can put a rho, R aluminum 0 is rho aluminum 0 times length of aluminum, delta T would be cancelling out from both sides, equal to minus alpha C rho C0 times LC. The corresponding data are given that enables you to find out what is the ratio of L aluminum to L carbon, and that works out to L aluminum divided by L carbon is approximately 227. So, these were examples where the series and parallel resistances were used. Let me give you a final example in series and parallel combinations. Let us look at a circuit like this. Look, there are too many of them. Well, let us number them. This is R1, this is R2, this is R3, this is R4, this is R5. Let us call this R6, R7, R8, R9 and R10. Doesn't look like a series or parallel combination, but let us try to look at this a little more carefully. So, all that I need to do is to observe whether the same current is passing through or is the same voltage between two ends. If it is former, it is a series resistance. If it is later, it is a parallel resistance. So, let us look at what is happening. Now, notice here, this point and this point, these 2 points are at the same potential, okay, and this is a common point. So, which tells me R4 and R5 are parallel combinations. So, let us write down R4 parallel to R5. So, let us denote their equivalent resistance to be R45. So, I will remove this section and put a R45 there. Now, the moment I have removed this section and put a R45 there, I notice R2, R3 and R45 are in series. So R2, R3 and R4, 5 are in series. So this section now, this and R4, 5 here. So R equivalent will be R, well this was already 4, 5 and I add 2, 3. So let's call this R2, 3, 4, 5. So this R2, 3, 4, 5 is obviously parallel with R7. So I write down that this is parallel there. Now once we have done that, let's call that, since the numbers are going on increasing, let's call that R7 prime. Now there what I do is this, that I replace this whole thing with the following circuit. It's becoming little clumsy, so let me redraw the equivalent circuit at this stage. This is V. I had a R1 there. This we called it R10. This was a R8 and an R6. So this is R10, R8, this is R6, and this we had called it as R7 prime. And there was a R9 hanging in here. So what do we have here? Clearly R8 and R6 are in series. R6 and R8 in series. Let's call it a single resistance R68. Not only that, notice that R10 and R9 have common points. So therefore R9 is parallel to R10. This we'll call it as R9 prime. So my circuit at this stage looks like this. This was R7 prime, this was R1, this is R9 prime, and this is R68. Now look at this circuit now. So what we find is that R9 prime and R68 are in series. And this combination, whatever you want to call it, let's call it R689. This is parallel to R7 prime. So therefore I can replace this with this resistance, an equivalent resistance, whatever you want to call it. So let's say it leads to some R prime, and then my R prime and R1 are in series. So therefore you notice a very complicated looking circuit has been reduced to series and parallel combinations. It is not true that always we can reduce any circuit to series and parallel combination. There are more complicated circuits for which we will find out the rules of how to do it in the next lecture. But let us proceed with whatever we have been doing. Now, so far I have talked about resistances in series and parallel. The only other element of the combination circuits that we have been using are batteries. So batteries or cells as they are called. So the question is this, that can we think of putting more than one battery in a circuit. So in other words, are the combinations like cells in series and parallel possible? I will of course give you more examples of this later, but let me try to define what is meant by cells in series and parallel. So first let's talk about cells in series. Now this has great practical applications. If you look up, for example, a laptop, now you will find that the laptop batteries are not single batteries. In fact, what you have in the laptop is a collection of cells, some in series combination and some in parallel combination. In fact, in many household applications, you use more than, for example, a normal torchlight cell. You don't use one battery. You put 2 or 3 cells end to end, with the positive of one being connected to the negative of the next one. So that is an example of something being in series. This is routinely done in all appliances at home, in your remote, for example. In your remote, you will find there will be 2 AAA batteries which are put in parallel. So let me first talk about cells in series. Now the cells in series are like this. Supposing I have an EMF E1 with an internal resistance R1. So this is your first battery. I will give you the way the combinations are used normally, that is positive end of one being attached to the negative end of the next one. So therefore, this is the way we would have it. So let's call this one E2 and internal resistance R2. So let us find out a nomenclature. So this is A, this point is B, and this point is C. Now what I am actually going to do is this. I am asking the question, is it possible to replace this combination with an equivalent cell? That is it equivalent to, between A and C, having a equivalent combination like this? This is AC. And if you like, I will call them as E equivalent and R equivalent. If it is possible to replace them, how do I do it? Now, let us look at this. Let's look at here. So, what is Vc? Now, if I assume that the current is flowing like this here and is coming in like this, then I look at the way the potential develops as I go from C to A. So I start with Vc. Since this is in the direction of current, I have a drop of current IR2. So current is the same, so IR2. Then I am crossing a battery from negative to positive, so my potential rises by an amount E2. I proceed further, have a further drop of IR1. So minus I R1. And once again, my potential is raised here in going from negative to positive to E1 until I have reached the point A. So this is equal to VA. So what is my VA minus VC? So VA minus VC is E1 plus E2 minus I R1 plus R2. So look at what have I done. If instead I had a single cell with an effective EMF of E and the total internal resistance of the pair were R1 plus R2, then I would have the same potential drop across the points A and C. So therefore, I can replace the system by an equivalent EMF, which is E1 plus E2 and effective internal resistance. Which is simply the two resistances added in series. I will in the next lecture talk about how to use cells in parallel. I told you that if you look up normal torchlight, you put cells in series. But look up your remote at your home, you will find that the two positive ends are going together on the same side and they are in parallel. So I will obtain an equivalent EMF and resistances for the parallel combination next time, and I will also answer the question which you must be already raising within your mind, that why should I use cells in series? For instance, why not I originally take a battery of a higher EMF and of course having a little more internal resistance. And so therefore, what is the purpose of using more than one cells instead of using a single cell of a higher EMF and different resistance? We will try to answer that question also as we go along next time.